Welcome to today's episode, where we're diving into a topic that's crucial for the backbone of modern technology: failure detection in distributed systems. As our reliance on technology grows, ensuring that these systems can handle failure smoothly is more important than ever. We'll explore how distributed systems detect failures, the various methods they use, and what these approaches mean for system reliability and consensus. In a distributed system, you've got multiple nodes working together to accomplish tasks. But what happens when something goes wrong? Failures can occur for a variety of reasons, like crashes, network partitions, or link failures. That's where failure detection comes in. It's essential for keeping the system intact and ensuring that all components can keep functioning. Failure detectors are the unsung heroes here, identifying when a node is unreachable or has crashed. A key insight in this field comes from the FLP impossibility result. This tells us that in an asynchronous system, no protocol can guarantee consensus. So, how do failure detectors help? They bridge the gap by enabling systems to make informed decisions about the state of nodes, even when some information might be unreliable. This balance between accuracy and completeness is fundamental to the operation of distributed systems. One popular method for detecting failures is through gossip protocols. So what exactly are gossip protocols? Think of them as a way for nodes to share information about their state with one another. This creates a network of communication that can effectively spread information about failures. Even if two nodes can't communicate directly because of a link failure, heartbeats, those periodic signals indicating a node is alive, can still make their way through other nodes in the network. While using gossip protocols does increase the number of messages flying around, it significantly boosts the reliability of information dissemination. This redundancy means that even if some nodes fail to communicate, others can still relay crucial information about the system's health. Now let's talk about the FUSE approach, which stands for Failure Notification Service. You might wonder why we need another method when we have gossip protocols. Well, in certain situations, propagating failure information to every node can be costly or impractical. FUSE is designed to provide reliable and cost-effective failure propagation, especially in cases where network partitions are a concern. FUSE organizes active processes into groups, which makes detecting failures more efficient. If a process within a group fails, all members of that group are quickly informed. This method effectively transforms individual process failures into group failures, ensuring that everyone is in the loop. The mechanics are pretty straightforward. Processes send ping messages to each other periodically. If one doesn't respond, the initiating process also stops responding to pings, creating a cascading effect that spreads failure information rapidly throughout the group. To visualize this, imagine a scenario with 4 processes chatting away. Initially, they're all alive and responsive. If one crashes and stops responding, the other processes notice and eventually stop responding too. Over time, this means all processes become aware of the failure, illustrating how individual failures can escalate to group failures through the absence of communication. Of course, this method has its pros and cons. While it ensures that all group members learn about failures, it can also lead to situations where a single link failure causes a broader group failure. Depending on the context, this could be seen as a drawback or a necessary safety measure. As we've discussed, there are various algorithms and methods for failure detection, each with its own strengths and weaknesses. Some focus on direct communication, while others use broadcast or gossip techniques. Additionally, some systems leverage quiescence, the absence of communication, as a way to detect failures. These diverse strategies highlight the complexity of failure detection in distributed systems. Whether it's through heartbeats, pings, or hard deadlines, each method offers different benefits, from simplicity to accuracy. The choice of which method to use often hinges on the specific requirements and constraints of the system at hand. Now, why are failure detectors so significant? They play a critical role in solving consensus problems in distributed systems. Research has shown that it's possible to achieve consensus even with failure detectors that might make errors. This flexibility is vital for developing robust systems that can adapt to changing conditions and maintain functionality even when things go awry. By leveraging failure detectors, systems can make more informed decisions, leading to a more resilient architecture. This adaptability is crucial in our fast-paced world, where systems need to operate continuously and reliably, even when faced with unexpected challenges. In summary, failure detection is a fundamental aspect of distributed systems, ensuring reliability and effective communication among nodes. We've explored various approaches, each with its own set of advantages and trade-offs, from gossip protocols to the fuse method. These strategies enable systems to detect and respond to failures, ultimately facilitating consensus and maintaining operational integrity. As technology continues to evolve, grasping these concepts will be essential for developers and engineers working in the field of distributed systems. We hope this episode has shed some light on the mechanisms of failure detection and its importance in building resilient systems. Thank you for tuning in, and we can't wait to explore more fascinating topics with you in future episodes.